Okay, so we're moving on to energy, and the next two chapters are going to cover conventional energy and sustainable energy. So this week we're just going to do conventional energy, which is chapter 9 in your book. So the first thing we need to talk about is measuring energy. So the average American home uses about 11,000 kilowatt hours of electricity per year. So what does that mean? So you've probably all heard of watts when you're buying light bulbs. This is for the standard light bulbs. Obviously this has changed a little bit with like the LED lights and things like that. But just so you can understand the idea, in 10 hours, the standard 100-watt light bulb would use 1,000 watt hours. And a kilowatt is just like a kilogram to a gram. 1 kilowatt is 1,000 watts. So your electricity bill is per kilowatt hour. So every time something uses 1,000 watt hours, so just the number of watts times the hours, you get a watt hour, and then you can get a kilowatt hour if you divide that number by 1,000. So that's the basic idea. And so just to give you an idea, this is how much energy some different appliances some of us might have use in about a year. And this is an average. It varies a lot, like how much you use some things. So like some of you may not even have a dehumidifier, or some of you may not use your stove at all. Or you may not have an electric stove. I have a gas stove, for example. I don't have one of these, so that's not part of my electricity use for the year. But a computer is basically about 100 kilowatt hours per year. Again, varies by how much you use it. Television a little bit higher at 125. 100 watt light bulb at 250. 15 watt fluorescent bulb, only 40. LEDs use very low amounts of energy compared to the conventional light bulbs that aren't even for sale anymore. Dehumidifiers about 400. Dishwasher is even more. Electric stove, it's producing all that heat you can imagine. This is much higher. Clothes dryers use a ton of energy. They're putting lots and lots of heat in to dry those clothes, and a lot of us use those pretty regularly. And then refrigerator, if you've got a full-size refrigerator, it's plugged in all the time, so it's using a lot of energy because it's constantly trying to keep our food cool. So just to think about energy consumption on the planet from different areas, the richest countries have consumed about 80% of all commercial energy, despite having only 20% of the population. So that is a huge disparity in availability of a commercial energy production. So 20% of the population consuming 80% of the energy. So by 2035, emerging countries like China and India are predicted to consume about 60% of commercial energy. This is because their populations are growing so fast, and they're trying to modernize as quickly as possible and get electricity to as many of their citizens as possible. Each person in a rich country consumes nearly as much oil in a day as the poorest people in the world consume in a whole year. So we've talked about some economic disparities, but the energy disparities are just as great as the economic disparities. You can imagine that someone that is earning less than $1 a day is not going to be able to have these kinds of appliances in their home or have electricity in their house or things like that. Interestingly, some countries like Norway, Denmark, and Japan have a higher standard of living than Americans do, but they do it using half as much energy. So that's really impressive, and we could really cut energy consumption if we could learn from some of the lessons that these countries have already figured out. So it suggests that we could keep our standard of living while using a ton less energy. So that's very encouraging. That means we don't have to produce a lot more energy. We could actually produce less energy and still have all the comforts that we've gotten used to. So how is energy used in the United States? So about 31%, a little less than a third, is consumed by industry. 41% is used for residential commercial customers, mostly heating and cooling and light. We live in Louisiana. We know how much it costs to cool our buildings in the summer. That uses a lot of energy. 28% of our energy is consumed by transportation. About half of the energy and fuels is lost during conversion, shipping, and use. So anytime we're converting energy, some is usually lost as heat. So if you think about your computer, if it gets a little bit warm, that's energy that's being lost, that's not being used to do all the things you want to do that are cool on your computer. It also is lost through the amount of pollution that's released. So global commercial energy production, about fossil fuels currently supply about 88% of the world's commercial energy needs. So how do we do this? If we think about a power plant, the average power plant produces enough energy for 640,000 US households or 1.3 million people in Europe. So I want to point this out. That's because US households use so much more energy than European households do. If we're going to compare this to renewable energy, about 250 wind turbines are equivalent to a fossil fuel power plant. And one fossil fuel power plant, though, is going to depend on a lot of mines, gas fields, train lines, if you're dependent on coal, or some gas can be transported by train, and pipelines, which is the primary way that we get natural gas and oil from place to place. So even though this sounds like a lot, one power plant to 250 wind turbines, there's a lot of other things that support one fossil fuel power plant. So it's not like this is just a whole lot more than that. There's lots of things involved in having all the materials needed to run a power plant. All right, so we're going to go through all the conventional fuels for power. Now, most of these are fossil fuels, but we'll also talk about nuclear power. And the first one we're going to talk about is coal. And so we talked about this a little bit when we talked about mineral resources. So coal is fossilized plant material preserved by burial in sediments and compacted and condensed by geological forces into this carbon-rich fuel that we use to burn primarily in power plants. Most of it was laid down in the Carboniferous period about 300 million years ago. So it took a really, really long time to form, and it's not a renewable resource. The Earth is not making new coal at any rate that would be at all useful to us. We're burning it much faster than the Earth can make it. However, there's a lot of coal on Earth. We have huge coal deposits. They're about 10 times greater than conventional oil and gas resources combined. So there's a lot of coal. We have talked about some of the negative implications of coal, though, which means that we definitely don't want to burn all of that. So where are these coal deposits? It's about a third in Asia Pacific, a third in North America, and a third in Europe and Eurasia. There's a tiny bit in Africa and the Middle East, and a tiny bit in South and Central America. But these three areas have most of the coal. So how does a coal power plant work? So we have a big pile of coal. It's loaded into the plant on a conveyor belt into a furnace or a boiler. The coal is burned. There's water piped through the boiler room to make steam. The steam turns the turbines, which creates electricity that goes out by the transmission lines. There's a condenser to recycle the water, and then there's also another condenser that cools the water, and we put the water back into the river. So some of the water is coming out of the river. So these power plants, because they need this boiler and they to run the turbines with steam, they have to be near a water source to function. So coal is not good. It's dirty, it's destructive, and it's very dangerous. So to get coal, we have to mine it. And there have been a ton of accidents mining coal. A lot of people have died. A lot of people have gotten sick. So between 1870 and 1950, more than 30,000 American coal miners died of accidents and injuries just in Pennsylvania. We also mine coal in West Virginia and Kentucky and some other places as well. And so that's just in Pennsylvania. Currently, China has the most dangerous mines. They have huge coal reserves and they have been building coal power plants. And just in 2008, they had 91,172 people killed in mining accidents. So really dangerous, not a safe job, not great for the workers. The workers that survive or don't have these accidents generally get very sick. So a lot of them develop what's called black lung disease, which you can see here. This is healthy lung tissue. This is people that have worked 10 years in the mine, and this is people that have worked 20 to 30 years in the mine. So you can see why it's called black lung disease. Literally, the lung turns black. And this is from inflammation and fibrosis caused by accumulation of coal dust in the lungs or airways. That basically means that the lungs aren't working properly. If there's coal dust in there, it's basically a type of particulate matter that's very damaging. So we talked about how when particulate matter gets embedded in your lungs, that causes you to have asthma and other breathing problems. It can make you more susceptible to respiratory diseases. People that live in places with higher particulate matter got sicker from COVID. So this black lung disease is no good, and it's shortening the lives of the people that work in the coal mines. Coal mining is also pretty destructive. So we talked before about how a lot of it is strip mining, where we're scraping the earth away. There's mountaintop removal that's frequently used in West Virginia, which you can see here, where they're literally taking the tops off of mountains. There's no vegetation anywhere. They're just trying to dig down and get rid of as much sediment as they can so they can get to this coal deposit and get it to a power plant so that it can be burned. There's also acid mine drainage. This stuff has toxic stuff in it, and so when it rains, the runoff off of these areas and from the piles of refuse are often very acidic, and it flows into streams and it can seep into groundwater. And there are also people that have gotten sick in areas near coal mines that didn't work in the mines, but their water was contaminated. So that's just the getting the coal out of the ground part. Coal is also creates a lot of pollutants when it's burned, and so that's obviously what we have to do if we want to use it for a source of power. So coal burning releases toxic metals and other pollutants into the atmosphere. Coal combustion is responsible for 25% of atmospheric mercury pollution in the US, and we know that mercury is a very harmful to our brains. It's a neurotoxin. Coal burning also releases sulfur and nitrogen oxides, particulate matter, and carbon dioxide. So if you remember, sulfur and nitrogen oxides contribute to acid rain. Particulate matter I just talked about can cause asthma, and carbon dioxide obviously causes climate change. Also, the ash from coal combustion is stored in these open storage ponds, which you can see here. And there is a risk of these getting into our river. So the coal power plant, we said, has to be next to a river to create steam. It has to have a water intake. So the coal ash is put in a pond here. If there is a major flood or an earthquake or something, this could breach and all of that coal waste could go into the river. So this shows the coal ash ponds, and it just shows how it could get into rivers or groundwater.